the cloud. So if I go too fast through something and you want to hear me say it 5 times more than I said it in class, then you can go back and watch the video and scrub it and go back and forth again. I will post that into Blackboard. Okay, so the other thing that I'm going to do is I'm going to do this in OneNote. Okay, I'm going to do my best to make everything legible and visible up on the screen, but you also, we've talked about this last time, my screen has an issue and it needs to be replaced or fixed. We've got the shadow across the bottom. I'm going to zoom way in, so hopefully you can see most of this while we're doing this. And I'm just going to fill in the notes today as we go. I may jump back and forth to a couple of places online to demonstrate some graph stuff whenever we get to that point, but you can fill in these notes. But the link to this notebook is also in Blackboard. And if for whatever reason you can't see this screen very well, you can actually log into Blackboard today and open up that notebook. I don't know how much of a delay there will be, but it will actually show up as I write on the screen. It will show up in that notebook as it goes. But like I said, there may be a little bit of a delay. Okay? Any questions before I get started? Okay, let's then dive in. I think this is still set up. Yes, so, and I can roll. Okay. So functions, the basis of what we're going to be doing in calculus when we work with the mathematics in here starts with mathematical functions. So we got to have a clear understanding of what a function is, because we're going to build from that concept. And so today, what we're going to do, if you kind of skim through the notes, section 1 is functions, and then we're going to look at a catalog of different functions that you need to make sure that you know. So we're just going to go through a whole bunch of parent functions and list those and some properties of those. Then we're going to go, after we get to that, functions from functions, how we combine functions to make new functions. That's like adding, multiplying, dividing, and subtracting. I left that one out. And composition of functions, which is plugging functions into other functions. Then we'll, at the end, talk about some special functions. This version of a calculus class is what's called an early transcendental presentation, which means we include our transcendental functions. That's a fancy name for exponentials and logarithms early. So we start from the beginning, and when we talk about derivatives, we already start talking about the derivatives of these functions too. Some calculus sequences will go through and learn all of derivatives and integrals and then come back and introduce those transcendental functions and then go back to derivatives. And so we do it early, okay? So again, I'm talking faster than I normally do. I'm going to fly through this. So what is a function? Okay, a function is some kind of mapping or rule that relates one set of objects to another set of objects. Okay, but there's a special rule that it has, and that every input to a function has exactly one output. Now, usually we'll be working with real number values instead of just generic objects, but functions can take other functions as arguments. Functions can map matrices to other matrices. Functions can operate on any kind of complex object. You just think of it as an input and there's an output. The function maps one to the other. Okay, they're typically represented by either tables or graphs, maybe even just verbal descriptions, but most commonly we will see them as formulas. But let's start with a graph, just so that we understand how this is set up. It's kind of hard to see, but this is the horizontal axis right here, and this right here, you see it labeled with the Y, is the vertical axis. You guys will recognize the rectangular coordinate system. We label points by where they are in their coordinates. X is the horizontal, that's the first value in an ordered pair for the coordinates of a point, and then the vertical is the Y. Okay, but when we think about functions, the input is the x-axis and the output is the y-axis. Okay, so when I say find f of 1, that's saying find the mapping, the output, the rule, when 1 is the input. So you go horizontally to 1, and what's the height of the graph? 3. If I say find the output of f is -1, then you go to x equals -1, and what's the height of the graph at that point? It's below, so you have to estimate here. What would you estimate that to be? Maybe -1/4 or -0.25. We know that it's between 0 and 1, and it's negative because it's down, right? I can reverse the question and say, what is the input, that is the x, whenever f of x is equal to 1? So the output is 1. You see how the notation is now flipped? Instead of having an input and we're trying to find the output value, we are given the thing that it's equal to, and we got to find what do we plug in. So we're looking then for a height of 1. So here's the height of 1. What are the inputs that give that height? X equals 0 and x equals, what'd you say, 3? So because 0 is right here, it has a height of 1, and 3 is right here. It also has a height of 1. Notice how the inverse question can be done backwards and can have 2 answers, right? The backwards question, that is, can have multiple answers, but the other question, the plugging in a number and getting an output, should only have 1 answer if it's a function, okay? You can also do it with formulas. You guys have seen this. I'll scroll this down so you can see it. If you've got a formula and you're asked to find f of 1, you plug in 1 everywhere there's an x and then simplify that expression using the proper order of operations. So f of 1 means not f times 1, but to plug 1 in, and plugging 1 in means everywhere there's an x, put the 1. I like, just to reinforce in my brain what I'm doing, to change the x's, the inputs, to parentheses, and then stick the number inside there and then go from there to simplify, right? PEMDAS, we do exponentials. There's nothing in the parentheses to do first, so parentheses, exponents, multiplication, division, addition, subtraction. You hopefully know those rules. We'll reinforce them a number of times. So I do the exponentiation first, then the multiplication, and then I'm going to add and subtract from left to right. 1 plus 3 is 4. Minus 5 is -1. Okay, so 2 important concepts that we talk about in the context of talking about functions is what is the domain and range of a particular function. Actually, I'm going to throw in a 3rd word in this definition. Coming back to the definition, thinking of it in terms of this mapping, a function that maps a set of values A. Let's draw a picture to help illustrate this. Draw a blob of something. Okay, it's just a blob, doesn't have to have a specific shape. This is just like a group of things, okay? The things inside there, there's like a bunch of points inside here. I'm going to map, I'm going to call this my set A, to another blob of things, okay? And I'm just loosely grouping them together and saying there's things over here, and I'm going to call this B, and I'm going to say, let's assign the rule that says this point, little a, goes to this point B, and I'm going to call that mapping or rule F. It's just another way to illustrate the general concept of a function, that F takes A as an input and maps it to B. Okay? So we call A a certain name. Okay? A over here is called the domain. Okay? So I'll write that in the blank. This is the domain. And don't be tricked into thinking that B is the range, because you've always heard range together with domain. It's not quite the range. It has a different name, okay? This whole set that we're going into is called the co-domain. Okay, so this would be the co-domain. I would abbreviate it that way. So then what is the range? Well, the range is what you get if you take every single point that's inside A, so there's a whole bunch of stuff over here, and you map them all into B. Where do they all go? Okay, it may be that there's points in B that don't have something mapped to them, right? You have extra stuff. Well, let's draw the picture like this. I'm going to draw a line this way and a line this way and say there's this little set inside here that all of these numbers map to. This goes to here, this goes to here, this goes to here. But everything that's inside A goes somewhere inside this inner circle, okay? But again, there may be things out here that nothing in A actually went to, okay? It's like whenever you have a function that is a graph, if I scroll back up, nothing mapped to a height of 3. So 3 would be in a codomain, but it's not actually in the range of that function, Okay, so we call this inner thing, I'll just write it as an R here inside there, but we call that the range. So the easiest way to think about domain and range is by looking at graphs. And we think of domain as the horizontal spread, how far from left to right is covered by that graph. Okay, and the range is the vertical coverage, how far from bottom to top is that graph. Okay, so if I go back up to the picture again, notice how the graph starts at this point. Okay, and it ends over here, right? So this would be the domain, because that's the horizontal spread or coverage of the graph, and it starts at this height and goes up to this height. That's the range. Okay? Now, in terms of numbers, notice the domain goes from a value of x is -2 all the way up to a value of x is, what is that, 4? Right? And it's everything in between. Like every value between -2 and 4 on the x-axis has a curve above it or below it, right? Corresponding to it as a height. Okay, so what I would say, if I wanted to write the domain down as an answer, what is the domain of that function? It starts at -2 inclusive and goes all the way to 4 inclusive. And the brackets mean include those numbers, right? And the range, I can't remember, you tell me, what was the range, looking back up at that graph, what's the lowest height that has a graph corresponding to it? -1, and what's the highest point? 3, and it would include those points. The way I would know it doesn't include those points if there was like an open dot at those points, and that's where I would do parentheses instead of brackets. Okay? So functions as tables, as formulas, and domain and range, now we know. One other thing that will come up quite a bit is properties that functions have. The main property I want to introduce to you now, if you haven't heard it before, you probably have. We talked about it in our trig class, those that had me for trig, that functions can be even or odd. Okay, it's a property that describes its behavior when you plug in a negative version of an input. So like if you have f of 2 and you plug in f of -2, if the function is predictable that you always get the same answer, then we call those even functions, right? No matter what x you plug in -x, you get the same number. Those are even functions, okay? Even. If f of -x is always equal to f of x. An easy example of an even function, and kind of see where the name comes from, is x squared. If you graph a parabola, notice that it's symmetric about the y-axis. Y-axis. Meaning that if I have a number, say, I don't like the size of this pen, I need to shrink it down a little bit. Say this value right here is x, this value right here would be -x, the same distance away. They have the same height, right? That makes it even, and that's true for everything. So you can tell something is even if it's symmetric about the y-axis, if it's a mirror image across there, okay? Other functions like, say, x cubed. Oh, that was a horrible line. Let me try that again. Undo. Oh, man, it is hard to use my little tablet here. I'm going to cheat. Shapes, line, look at this. Wow, he's so straight. Woohoo! Okay, this one. And that's so straight. Okay, so a cubic would look like this. It's almost like a parabola where you broke the left-hand side down. Okay, that's like x cubed. So this is an example of an odd function. And odd functions have the property that f of -x is the same thing as negative of f of x. That you can pull the negative outside and you get the same answer. So in this picture, what that looks like is if this is x and this is -x, meaning it's the same distance away, this could be 2, 5, 7, whatever, but if you go the same distance the other direction and you look at the height of the function and the height of the function, that they're the same height, but one's negative. Below, right? Negative, okay? Or if it's below on one side, it's above on the other, right? So what the way we describe that is it's symmetric about the origin, which means it's like a flip two directions. You flip it this way and then you flip it this way. boom, boom, right? Can't do that, man. So, and then flip it this way, okay? So if you look at these two graphs right here, functions can be even, odd, or neither. Is f even? And just look at this question right here. Is that symmetric? Is it a mirror image across the y-axis? It's the same on one side as the other. It's not, right? So it's not even. Is it odd? It kind of looks odd, but the problem is where the x-axis is, right? So it does look like it's flipped and then flipped, but it's flipped about this like height up here. But that's not where we flip it. We flip it about the x-axis. So the other side would have to be somewhere down here. So it is neither, right? It doesn't flip and flip because it doesn't go all the way mirror the x-axis, but it does, and it doesn't actually just mirror the y-axis either. But what about G? What would you say about G? It is even because it is a mirror image across the y-axis. Very good. All right, so that's section 1, properties of functions. Let's now look at our catalog of functions, okay? A bunch of functions that you should have seen in Algebra 1, Algebra 2, and trig. I left out trig functions. I just now realized I did not put them in here. Trigonometric functions are those sine, cosine, and tangent values. But let's start with kind of the parent of all parents, the simplest of all functions, like x. If you have x to a power, that's called a power function. Okay, very simple. X squared, x cubed are all power functions. What is the power on x if it's not there? 1. And we give this a name. It's called a linear function. Can also be called the identity function when it's just x. But in terms of the degree of that power, we think of it as linear. You graph it, it's a line. Okay. The second one we call the squares. Remember the word? Quadratic. Ooh, can't spell. How about QU? And 3, cubic. I could go on. 4th is quartic and quintic. And I don't know if there's one for 6. I guess it could be sextic or sextic or I don't know. At that point, we just start saying degree 6, degree 7, degree 8, and so on. Okay, sometimes I'll just even say degree 3 there. So the domain of these functions, the thing that I can plug in, okay, that allows me to get a value out of it, how much spread there would be horizontally, every x value that can be an input to these, is actually all numbers, right? I can plug in anything to any function that looks like this, okay? So long as a, by the way, is greater than 0. If a is negative, then we have a restriction on the domain. But I just want to think about the power functions that are positive. Okay, so the domain is everything. The range varies based on whether you've got even powers or odd powers, and you can see that in the picture of the graph that I have below here. The function that goes down, this f right here, that is x cubed. The blue function, which I know your notes don't have this, but you can see it in the picture here in the notes online. You can at least label it. This h right here, okay, that's x squared. That's the parabola you've seen before. And then this guy right here, the green one, notice how that green is like a parabola, only it's flat, squished. When you raise higher and higher even powers, it just gets flatter and flatter until it almost becomes like this U, like a very square looking thing, okay? But that's what happens with those. But notice what happens on the left-hand side of the even ones, the x to the 4th and the x squared, and even if x to the 6th, is that it goes back up, right? Which means the vertical coverage, the range, only starts at 0 and goes up, which is where I came up with this, right? The range for even degrees is 0 to infinity. The range for odd degrees, like f equals x cubed, would be all real numbers, that is from negative to infinity to positive infinity. Okay? Most of the homework questions in this section that you'll have will ask you for the answers in interval form, which is why I'm writing it like this, right? Think of intervals like I wrote from -2 to 4 or something like that above. You can put brackets or parentheses. Well, if you want to do all numbers, you use the infinity sign, which means keep going in that direction, left or right. Okay. Another notation for this that we will use quite a bit in here is just to write it as set of all real numbers. It looks like an R. Okay. These two are the same thing, but this is the way we write it as an interval. Okay, so that's the power function. And you got a little bit of guidance as to which one are which and how they look as graphs based on the power. Odd powers do go down to the left, right, to the left, and up to the right, but even powers go up in both directions. Okay, now polynomial functions takes power functions and adds them up or subtracts them and puts coefficients in front of them. Okay, so notice that this kind of messy general form is how I would write down a polynomial of arbitrary or general degree. So like, let n be any number, this is what it would look like. That it starts with x to the nth power and then goes all the way down x to the n minus 1 power to x to the first power to no x at all. So like if you have this third example here, x cubed starts at the highest degree and goes all the way down to x to the 0. Okay, so these are what they look like in practice. This is just the way that I kind of generalize them to write down a general polynomial. But it is a combination of power functions. Okay, but we give them the same name. Okay, you look at the highest degree term is the polynomial degree. I'm just going to write that off to the side. That helps us fill in these blanks. Like, what would you call this type of function? I would call it linear again, because the highest degree term is the first power, which was the exact same name we gave x to the first above, and they graph as lines, right? And then this one is quadratic, because the highest one is x squared, and this one is cubic. The domain, the set of all inputs, is all real numbers again. You can plug in anything. Okay. The range, if it's an odd degree, it's still the whole vertical range. That is all real numbers. You can get to every output if you have an odd degree polynomial. Okay. But if it's an even degree polynomial, it's going to be restricted. Okay. But where it either goes up for half of the line or it goes down for half of the line or half of the vertical range, where it starts and goes up or where it starts and goes down depends on the polynomial. So it varies by polynomial. And just think of it this way, like you got a parabola. I'll put this on screen so Grant can see. Put the parabola like this, right? Well, you can move parabolas up and down by changing what the added term is at the end. Okay, you can make them wider, you can make them narrow, but they still go forever in both directions. Okay, so it doesn't change the domain, but you can also flip them, right? So it's upside down, right? And then your range is from some number, from negative infinity up to some number. So that's why it's different every time. Okay, so the domain and range, the easiest way to figure that out, look at the graph. You can graph the function, you know, throw it into your graphing calculator or into Desmos.com or Wolfram Alpha or some kind of online graphing tool, which I'll show you Desmos before the end of today. Then you can figure out the coverage, vertical and horizontal coverage. That's what domain and range help you figure out, but you always have all real numbers. Okay, so we're building up from there. So we start with power, we built up to polynomials by combining them together. If we divide two polynomials, we have what's called a rational function. So if you have a polynomial on top and a polynomial on bottom, then it's called rational. Okay, in your mind, from this point forward, as a math major or math-related major, computer science teaching, whatever you're going to do, rational in your mind should mean the same thing as fraction. Okay, that's our fancy word for fraction. So a rational function is a fraction. Okay. But fractions with polynomials inside. A rational number is an integer divided by an integer, right? So that's just what rational means. It doesn't mean of sound mind, you know, thinking logically, not in our world. It means fraction. So I don't know why we couldn't just use fractional, but, you know, I inherited this terminology from the mathematicians that came before me. That's what we do. Okay, so this is an example of a rational function, and if I ask you to find the domain of something like this, you have to think through, what can I plug into this that actually gives me a legitimate value and output? And up to this point, everything was allowed, but now we have a problem, and it's the old divide by zero problem, right? If you plug in a number that makes the denominator 0, you have no output, okay? It's undefined. So we can only include in the domain the values that have a legal, legitimate output. So it's going to be all reals except where the denominator is 0. If I ask what the range is, it's going to vary depending on the rational function, and the graph is generally the best way to determine it, although we can get a little bit better than that later in this class. So what is the domain of this function? Well, the way that I would figure that out is to find what makes the denominator 0. So first, figure out what x would be that makes the denominator 0 by setting 7x squared minus 3 equal to 0. And then solve that. Okay? Whatever tools you have for solving, you can add 3 to both sides. You get 7x squared equals 3. You can divide 7 off both sides, right? And you get x squared is equal to 3/7. Then you do what? Square root. But there's a rule you got to remember to do when you take the square to both sides. You have to include plus or minus because both values squared to give you that 3/7. So it would look like x is plus or minus the square root of 3/7. Now I am not, and I don't think WebAssign is picky. Sometimes it may be picky about rationalizing these things. That's where you have to make sure that the bottom doesn't have a radical in it. I'm just going to leave it like it is for now. So that means there's 2 values that x can't be, right? So your domain is everything where x is not plus or minus the square root of 3/7. If I wanted to write that in interval form, think about what that looks like on the real number line. Here's 0. There's some value over here, negative square root of 3/7, and some value over here, positive square root of 3/7, that have holes there. You can't include that, but everything else is allowed, right? So everything except those 2 numbers can be plugged into that formula above, and you will get an output because you won't get a 0 in the denominator. But if I plug those in, I can't. So if I wanted to write it as an interval, I would write it like this. Okay, I would take negative infinity up to negative square root of 3/7. That's the first interval. I would take a union, and I would go from negative square root of 3/7 to positive square root of 3/7. And then I would take a union of, that's 7ths right there, sorry. Square root of 3/7, all into the radical, all the way up to infinity. So you got 3 intervals together. That's how you would write it in interval notation. So you can see how this is probably a preferred way to write it, but this might be asked for just so that you understand how you can connect interval with domain where it's not equal to some value, okay? So the more complicated our functions get, the more complicated the process of finding what's allowed to be plugged in is, and it usually boils down to, zeros and denominators. Another problem we run into is if we introduce root functions. So the next section is root functions. That could be any root, like square roots, cube roots, fourth roots, higher roots into some positive integer. This is what the notation looks like whenever there is no n. What is n assumed to be on a root that doesn't have a number up there? You may be tempted to say 1, but it's not 1. That's whenever it's no root at all, x to the first power, right? But if there's nothing there, then it's understood to be 2 here. So n is 2. And we call that the square root. And you should know what that means. It's finding the number that when you square it, when you raise it to the second power, it gives you the number inside, right? So like this over here is an example of a graph of the square root of x. And you can see that if I go to, say, 4, what's the height of the curve at 4? It's 2, because that's the square root of 4, right? But there's nothing to the left. There's no real values to the left. And why not? Because you can't take the square root of -1 and have a real number output. You have complex numbers, which we're not going to touch on today, but we will eventually see some stuff about complex numbers. Actually, really not this semester, but next, if you take Cal 2. So looking at this picture, what's the domain and range? Well, you can see the picture gives us horizontal and vertical spread. So horizontally, it starts here and goes to the right, which means I would write that as 0 to infinity. That's the domain. And actually, that's also the range in this case. Maybe I should write it twice. That's domain. And then the range is also 0 to infinity. Yes? Okay. Again, there will be a lot more time for questions and stuff like that. If I flew through past something, you know, in later sections, we're going to take time to dig deeper if we need to. Just not doing that so much today. This one you may not have known the name for, but it's like when we introduced the rational functions, we had polynomial over polynomial. If you have a polynomial inside of a root, that's what's called an algebraic function. Actually, algebraic simply means a mix of exponential, multiplication, division, addition, subtraction, and roots. If you have any combination of those, that's algebraic, okay? And what we will move on to later, you know, from this point forward, is things that involve new things, like putting variables in the exponent or including logarithms or trig functions. Okay, algebraic is all the normal algebra operations: addition, subtraction, multiplication, division, exponentiation, and roots. Okay, that's algebraic. So I may use that term occasionally, but now you know what it means. So root of a polynomial is the easiest way to think of that. And the set of all values that we can plug in, okay, you've got to be when n is even. It's everywhere where the inside is greater than or equal to 0, right? Because you can't plug in negative numbers into an even root and get a real number out, okay? And I should have put this in here, but if n is odd, then the domain is actually easy. Domain is negative infinity to positive infinity, if n is odd. Okay, the next parent, exponential functions. Okay, it's b to the x, where b is just some number. So we're talking like 2 to the x, 3 to the x, 4 to the x, maybe 1/2 to the x, 1/3 to the x, 1/4 to the x. Those are all examples of exponential functions. It's important for you to see the difference between that and power functions. Right? A power function has the variable down on bottom and a number up top. And an exponential function has a number on bottom and the variable is in the exponent. Okay? Exponential means that's where the variable is. It's in the exponent. Okay? The domain for all of these is the entire real number line. You can plug in any number into one of these x's and get an output. The range for all of them starts but does not include 0 and goes up. Okay, and you can see that from all of these graphs. So I have graphed on here several different exponential functions. So look at the red one. You see the red one is kind of the, other than the blue, it's the highest one on the left-hand side, and it's the lowest one on the right. It's kind of the slowest growing one on my picture here. The red one, that one right there, is 2 to the x. And you can see that by going and looking at, okay, if I plug in 0, 2 to the 0 has a height of 1. Anything to the 0 power, it's 1. If I go over 1, then I'm at a height of 2. So that's 2 to the first. If I go over 2, I'm at a height of 4. That's 2 to the second. That's 2 to the x. Can you guess what this one is? If I go over 1, how high am I? 2, 3. So that's probably 3 to the x. It gets steeper the higher the base. This blue line, which you can't really see on yours very well, maybe it's gray there, right? But that's 1 to the x. By the way, 1 to the x is actually just 1, because 1 raised to anything is 1, right? You multiply 1 by itself, however many times, you're still going to get 1. Take the square root of 1, you get 1. So it's always a height of 1, okay? And now if you were to take 3 to the x and kind of flip it around the x-axis, that's the 1/3 to the x. And this one over here is 1/2 to the x. So notice values between 0 and 1 go downhill when you have a base, and values from 1 and above go uphill from left to right. That's increasing from left to right. Okay, got those? So those are the exponentials. Now, logarithmic functions, let's just assume for this moment that you have a log button on your calculator and you're going to hit it. Let's not talk about what log means until just a little bit later in the class. I know we're getting close to the end, but we will get there at the very, very end. Logarithm, okay, if you have a log base b of x, okay, this is the logarithmic function. Whenever you see the log in there, you might occasionally see this also means log or log with no base. We'll come back to it, but this means b is the number e, and this one means b is the number 10. But those are all examples of logarithmic functions, okay? And logarithmic graphs look like exponentials that have been flipped along the diagonal. Like if you were to take a diagonal line through here, right? If you took any one of those exponential curves and flipped it along that, you end up with a logarithmic curve, okay? Okay, because it's kind of like a sideways exponential. You turn your head on its side, that's what it looks like, okay? So this red one right here, the kind of shallowest one, that's log base 2 of x. This is log base 3 of x, and then log base 4 of x. And the red one down here, which is now the bottom curve, would be log base 1/2 of x. And this is log base 1/3 of x, and this is log base 1/4 of x. Now that's kind of hard to see, but 1/2 is the bottom, 1/3, and then 1/4. And just squeeze in down here. Trig functions mean sine, cosine, tangent, cosecant, secant, and cotangent functions are involved. We will do a little bit of trig review when trig shows up for the first time. The main thing you need to know from trig is graphing those functions and how to evaluate those functions. Things like unit circles and maybe triangles like SOHCAHTOA. But like I said, we'll revisit that the first time we have to use it, just to refresh your memory. Okay, so functions from functions means that we can take functions that are given to us and do things like add them up and create new functions, or multiply or divide or subtract them. And so this example right here is a problem that's on your homework where you're asked to find f plus g and f divided by g if you're given the two functions. And hopefully it's something you've done before. It's as easy as it looks, right? If I say f is x cubed plus 4x squared and g is 7x squared minus 3, then f plus g as a new formula, a new function. That's its name. Means to take whatever f of x is and add to it whatever g of x is. Which new formula is x cubed plus 4x squared. That's your f. And your g is 7x squared minus 3. You just add those two formulas together. And then if you simplify that by collecting like terms, you get x cubed plus 11x squared minus 3. That is f plus g of x. And by the way, his domain is everything. And that's because there's no denominators, there's no roots, so there's no restriction. So what do you think you'd do to do f divided by g? What do you think that symbol means? Not quite. If I wanted to subtract, I could do this, right? That would be to subtract them. So what do you think putting one over the other would mean to do? Yeah, so just write it almost like it's written right here. Put on top of the fraction bar the f function, which is x cubed plus 4x squared, and on bottom the g function, which is 7x squared minus 3. There's your new formula. And if you ask for the domain, I'm going to say we actually already did that problem, intentionally so. I asked you for the domain of this function earlier in the class, and it's that interval one up there above. I won't leave the screen yet, but it's the interval one above. Okay, so algebra of function just means, can we add, subtract, multiply, and divide formulas? The answer is yes. Just combine them the way that you would do if I wrote the plus sign between this formula and this formula. Okay, so we can combine and make new functions from old functions. Another way that we can make new functions from old functions, and this gets a little bit confusing the first time you see it. Hopefully you've done it before, but I'm going to at least show you the notation one more time and let you practice once in the homework. This little circle, does anybody remember what that means? It's not multiply. If I wanted to multiply, I could write one of two things. You're close. It looks very close to one. Like I could do f dot g, and notice how little circle and little dot look close to each other, but dot means times. Okay? Or I could just write f g. Both of those mean multiply. So I can see where you would think that looks like a multiplication. But what is it if it's an open circle? Does anybody remember?
Insert it.
Insert it. That's exactly right. You remember the name? Yeah, exactly. So that's what we mean to put one into the other is f of g. There's a name for that. It's called, anyone? It's called composition. We like to assign some big fancy word to a very simple idea. It's to plug one into the other. So we plugged numbers into functions before, right? We plugged in 1 at the very beginning of class and evaluated the function, right? Well, now we're going to plug functions into functions. Okay, so f0 or a little circle means f composed with g. F composed with g means, right, that's the name of the function. It depends on x, so I write it as f composed of g of x is f of g of x. Okay, and what's inside these parentheses is what goes inside the x. So this looks like f of, what's g? G is this guy. So x squared plus x. And whatever's inside these parentheses is what goes inside the x over here. So we're going to take this and stick it in where that x is. So this looks like 7 something plus 6, and this x squared plus x is what goes inside there. You see how all I did was I changed the x to parentheses and then stuck inside what I was going to plug in. Before I plugged in a number, now I'm going to plug in a formula, and now I've just got some simplifying to do. 7x squared, multiply that out, plus 7 plus 6. So my new formula is 7x squared plus 13. Okay, that's f composed with g. Thank you. So that no longer does this. Thank you very much. I like to make mistakes so that you can catch them. I will not lie to you and tell you that was intentional, but absolutely, I make a lot of mistakes. Every mathematician makes a lot of mistakes. About 50%, 70% of the time, you're fixing your mistakes. You're debugging. I'm a computer science guy, so I think in terms of bugs in my code, bugs in my arithmetic. Help me fix it. Okay. If you see something that looks suspicious, if we leave it on there, I could end up in a completely wrong place by the end of the lecture. And if you caught me before that, then we wouldn't have to go back and redo the whole thing. So thank you so much for catching that. All right, exponentials and logarithms. Guess what? I don't have time to do this right now. Let me fill in the blanks real fast. And then if you have questions over the homework, you can ask me. But this natural number is 2.718281828495. ... It's a special number that makes sure that this function b to the x has a slope of line, a slope of 1 for that tangent line. That was interesting. And then we'll come back and define logarithms next time. Let me do this real fast. So logarithms are inverses. Y equals log base b of x is the same thing as x equals b to the y. To y. This is x, this is x, this is 4, and this is 1/3. And then I'm going to leave the last two examples. You are dismissed, so you can grab your stuff and go. I am going to fill them out on this video real quick, so that if you watch the video, you can go skip to the very end and see me work these two examples out that are in your homework. Okay. If you have time to stick around for 5 minutes and watch me do it, you can, but if you've got class, please go, okay? I'm just gonna really fill in the blanks, not really do a lot of explaining, but I will go ahead and mention a couple things here. So let me pause for a couple minutes for those of you that need to go, can go, and then I'll keep moving forward. I won't do this usually. I will finish at 10 till, but I wanna get these on the notes. Does anybody have class right now? At 11 to 12:15? None of you? Okay. All right. I'll go fast. I promise. Not too fast, but the same level of fast. Okay. So logarithms are the inverses, the reverse of an exponential. It's the thing that cancels. Like square roots cancel squares, divide cancels multiply, subtraction cancels addition. We need things to undo things, especially when we're solving equations. Because when you solve equations, you're trying to get things by this all on the same side. If you have a plus something, you need to subtract it to the other side. You have a square, you need to square root it. If you have an exponential, you need to get the variable out of the exponent and down on the base. You got to undo the exponential. Logarithms are what undo exponentials. So to write down y equals log base b of x is the same thing as writing that the base raised to the other side is the inside of the logarithm. Okay, and that makes this problem down here easy to see why it would be 4, because you're asking, what do I have to raise to in order to get to 16? What's the power that I raise to get 16? 2 to the what is 16? 4, right? So this is the answer to 2 to the what is 16. This is the answer to 8 to the what is 2. Doesn't mean divide, it means what do I raise its power to? and we probably should have mentioned this earlier, you have seen this before, but you're actually taking a root to get down here. You're taking the cube root, right? It's the cube root of 8 that gives me 2. And cube roots are exponentials with fractions in them, 8 to the 1/3. That's why the answer is 1/3. Okay? So that's how you actually figure out the value of logarithms, is to ask the question of the base to the what is that number. And then when that's asked like this, okay, if you cover up the base 2 right here and just look at log base 2 of x, and then I raise 2 to that power, notice that's kind of asking the same question twice. 2 to what power is x? And whatever the what is, raise 2 to that, what am I going to get? The answer is x. They cancel each other out, right? Because this log base 2 of x means 2 to the what equals x, right? What goes in here is the value of this, and if I raise 2 to that, then I'm going to get that x. That's why that works out. And natural log, the ln of e to the x, that's log base e of e to the x, because natural log means log base e. They will cancel each other out and you get just x. Logs and exponentials, if they have the same base, cancel. So it's not even like suspended up here in air as an exponent anymore. It's just gone, and it's now just the x. Okay? So that's what logarithms mean. The base to the what equals the number inside. And we then use that to solve these equations down here. We're going to take logs of both sides or exponentials of both sides to cancel things. So the steps for solving an exponential or a logarithmic equation is to get the exponential or logarithm by itself. Let's isolate it. Then take either the log if it's an exponential, or take the exponential if it's a log, to cancel out that logarithm, or to cancel out the exponential. I'll show you what that means with these two examples, okay? And then solve for x. So on this one, I would take the log of both sides because it's got a variable in the exponent. So to get rid of the variable in the exponent, I'm going to take the log. I'm going to take the log whose base is e of both sides, which is the natural log of both sides. Natural log of e to the 3 minus 4x is 5. And then natural log of e to something cancel. Just like we saw up above in that blank, the log of e to the x cancel left behind the x. Log of e to the 3 minus 4x will leave behind 3 minus 4x. And this should have a log right here. Sorry, I said both sides. You got to do both sides. Log of the 5. Don't forget to write that. That's not an H. It's bad handwriting. Try that again. Equals natural log of 5. Equals the natural log of 5. That's a number you can get out of your calculator. Okay? If you subtract 3 from both sides, you've got negative 4x equals natural log of 5 minus 3. You divide both sides by negative 4, which means your answer is x is natural log of 5 minus 3 over negative 4. And this, yep, that's it. Oh, yeah. I hope there's not a class in here. No, there's not, because we have the Monday lab time. You know what I'll do? I'll give you back these 10 minutes during our lab on Monday, so that like I'm not stealing your time away from you. Okay. So that's that one, and then let me do this example, and then I'll stop the video, and if you have any questions at all, I can stick around and answer them. So this one up here had an exponential, and so I took the log of both sides. This one has a log, which means I want to do this. I want to take the exponential of both sides. What does that mean? That means to raise both sides. Like if you have this equals this, to take an exponential means to raise both sides into the exponent. Okay? Now, what's the base of the natural log? It's not 10. If it was log, that's the common log, that's 10. So if it's the ln, or the natural log, it's the base e, okay, that e number. So what I'm going to do is I'm going to do e to both sides power, right? So I'm going to write the left-hand side as e to the natural log of 3x minus 10, and the right-hand side as e to the 9th. That's what it means to take the exponential of both sides. By the way, the nice thing about these two problems is I already did step one. Step one was to isolate the exponential or logarithmic expression. So like I got just that expression by itself. It's already by itself, so I didn't have to do anything there. And so what does e to the natural log do? Cancel. You have 3x minus 10 equals e to the 9th. E to the 9th is just a number in your calculator, but we'll leave it in this form. I add 10 to both sides. 3x equals e to the 9th plus 10. And then divide both sides by 3. X is e to the 9th plus 10 divided by 3. Booyah. So, here, there. Goodbye.